So before I go through this solution, I think this solution is technically incorrect, very slightly incorrect. And the reason for that is this thing is going to spin around, A is going to spin around until this cable gets tight. And then it says that that cable snaps tight. And then so it will look like this when it snaps tight. And the reason I think this is wrong is that red line I just drew is not exactly horizontal because that one radius is smaller than the other. So this is not true here on this side. This is not horizontal and that's not horizontal. And that will slightly affect the solution, as we'll see later. But I'm going to solve it assuming those two tensions are horizontal, and we'll proceed from there. So this is actually a pretty tricky problem. I solved it as momentum, but as I said earlier, for reasons I'm going to explain, it's not exactly right because of the angle of that string. But anyway, so momentum, the reason I think it's momentum is it's like an impact problem. It's like that string is impacting A and B, but it's internal to the system, and so it does no net momentum. And we're given the velocities, angular velocities before, and it wants to know the angular velocities after. So it's just like, you know, block A slides, hits block B, they stick together and they both go, what's the new velocity? So it's just like a momentum problem, but it's spinning instead. So what we have is before, block A has a momentum, angular momentum of I times omega, and block B, which is not spinning yet, has no angular momentum. And afterwards, they're both going to be spinning because the cable is tight. And for kinematics, we can figure out what the relationship between the two omegas are. But what makes this problem interesting and actually potentially wrong is this part right here. Okay, I've drawn in picture what happens. When that thing yanks tight, all kinds of things are happening. Basically, it induces a reaction at these two pins, which are hard to see in a picture. There's a pin there and a pin here. And that reaction, there's actually a Y and an X component to that reaction. And we'll talk about that. So, but anyway, if the tensions are horizontal, okay, and you look at this free body diagram here, there is no Y acceleration because it's pinned. So you can see that AY equals 30 pounds. They have to be equal. Because T is horizontal, there's no Y component to the tension. And in this case, BY will equal 15. So the reaction counteracts the weight perfectly. This is not true because T is slanted, and so there's a slight component of T in both of those reactions, so they're not quite equal to 30 and 15. But for now, we're going to say that the reaction here is equal to the weight, and the reaction there is equal to the weight. Okay, now that we've gotten that out of the way, you have these three pictures, and you have to do the same thing to all three pictures, and you have to take both of the wheels with the string included as a unit. So what I'm going to do is I'm going to take moments about right there. So on the left, then I'm going to take clockwise positive. So in the left picture, the moment about the middle is IA times 6. No problem. On the right picture, it doesn't matter where you take the moments. If all you have are these moments, you're just going to get IA times omega A prime, meaning after, and IB times omega B prime, after. So the big question is then, what is the moment about there? And so assuming that the center of the hubs are at the same elevation, that goes right through the middle, that has no moment, and assuming that the normal force up, the reaction up, is equal to WB, there's no moment due to these two forces because they cancel out, and so this integral, there is no moment about there, so it's 0. So we just have 6IA equals IA omega A prime plus IB omega B prime. Okay, and then the kinematics, what we're going to do is the velocity of that string is omega A prime times the radius to the string of 1.2. It's the same string, so it's also equal to omega B prime times the radius over there, which is smaller, 0.4. To the string. And so you solve that, 0.4 times 3 is 1.2, so you solve that for omega b is 3 omega a. And so all you have to do is put in for omega b prime, 3 omega a prime, and you can immediately solve this equation for omega a prime. Of course, you need to get I of a and I of b. They I think, give you the radii of gyration for both of those. Okay, and once you solve for omega a prime, 3 times that is omega b prime, and you're done.